It's always a pleasure to visit these AutoML events, AutoML Summer School, AutoML Conference, and excited to share our recent work on time series forecasting with you today. So today we'll talk about a few things. We'll start by just giving an overview of what forecasting is, what traditional forecasting models do, and how they work. We will then move on to our work, talking about our work on Chronos and pre-trained models for time series forecasting, which is like a new class of model that recently started appearing and has shown some pretty impressive results. And finally, we'll talk about some future directions of our work in the world of time series forecasting, and we will see how AutoML can play a very important role moving forward to getting better time series forecasting methods. So first, let's talk about some basics and cover some, background material. In general, when I talk about time series, it just means that we have something that we measure over time, usually at regular intervals. Such data comes up in a lot of different applications in many different industries. So for example, in energy, you can think about the energy consumption of different people, and that at different hours of the day, we have different energy consumption, and it's important for the energy company to know how much energy will be consumed at different times to make sure that they can satisfy the demand and everyone can do what they need to do with the energy. Also comes up very frequently, for example, in retail, where you want to maybe sell different products and you want to make sure that we have enough items in stock. Also other cases like healthcare, traffic, weather, all of these different domains have these cases where we measure something over time and we care about how things are changing over time and what happens in the future. When it comes to different machine learning tasks for time series, there are also lots of different cases. So, maybe in general, when we think about machine learning, time series is more like a footnote where it's like, okay, we mostly work with tabular data, but there's also time series, but it's not that different from tabular data, so don't worry about it. But in reality, there's a lot of stuff related to time series and also lots of different machine learning tasks that people care about. And the first one that will be the focus of this talk is forecasting, where we want to answer the question of what will happen in the future given the past. But there are also many different ones. For example, anomaly detection, where we want to find something that goes wrong over time. Classification, where you want to look at the entire time series and answer if it's, how different entire time series belong to different classes. Maybe heartbeat time series of a healthy patient versus a sick one. Clustering, where we want to find groups of related time series. And also imputation, where we have not observed the data for some time and we want to figure out what happened in this time interval. But today we'll mostly talk about forecasting and about machine learning models for forecasting. In general, the main question that we want to answer in time series forecasting is what will happen in the future given the past. Back to this example that we considered before about demand forecasting, maybe you are some company that you have a company that sells some products. You want to know how many items of each product will be bought in the future to make sure that you have enough items in your inventory to satisfy this demand. This also applies to all the other cases. Maybe you want to predict the stock price, maybe you want to predict the energy consumption, maybe you want to predict the weather, the temperature, the amount of precipitation for the future. All of these different problems can be formulated as a time series forecasting problem. And the way we usually approach them in practice is by using the language of probabilistic machine learning. We often talk about probabilistic forecasts. It means that our prediction tells us something about the distribution of the future time series values given the historic ones. So in the most general case, we want to reason about the entire conditional distribution of the future values. But in many practical cases, we don't really need to go all the way to these complex, high-dimensional distribution objects. Often it's enough to just look at a point forecast. And the point forecast just means that we predict a single time series value for each future time step. So in case of sales, maybe you will say, I expect to sell 200 items tomorrow, 100 items the day after tomorrow, and so on. This will be a so-called point forecast, which, for example, can be the mean of this conditional distribution of the future values. Another way to talk about these forecasts, if you want to talk about the probabilities and the range of possible outcomes, is to consider quantile forecasts, which kind of tell us about the range of possible outcomes. So instead of just predicting a single value in our forecast, we might predict different quantiles separately. So for example, in demand forecasting, we can say we predict that there is a 90% chance or 80% chance that the sales tomorrow will be between 190 and 220 items. And this allows us to reason about the range of possible outcomes. And this is also very important in these different planning problems, to kind of look at this uncertainty in predictions and use that to make the decisions that respect all the different possibilities in the future. So now, after we have looked at this general problem formulation for forecasting, when talking about the conditional distributions, let's see how this is often done in practice. In general, there exist two main classes of models for time series forecasting. The first one are so-called local models. And these are, like the very famous examples are maybe statistical models, or also called econometric models, such as ETS, ARIMA, or theta. And these models essentially work in the following way. You fit a single model for each time series in your dataset. So maybe if you want to forecast sales for 100 products, you would need to fit 100 models, each model for a single time series in your dataset. And this model usually captures some very simple patterns in the data. One such pattern would be seasonality, which means that time series have this, this tendency to, repeat themselves over time. So for example, the sales next Tuesday are probably similar to the sales from previous Tuesday, but they might be different from the sales on Fridays. Which is why you always have this sine wave-like behavior in time series that is called seasonality. You can also have other things such as trends, where things slowly change over time. Maybe your company is becoming more successful, you sell more products over time, so you have a slow trend that goes up, that keeps going up. And some other things like autoregression, where the value tomorrow is similar to the value of yesterday, or like the average of the last couple of values. Lots of different simple patterns, but they're all quite simple, and usually we just directly specify them by hand in these models. So for example, ETS, we have the trend and seasonality that just directly put in there, and we fit we have some parameter corresponding to the seasonality, we have another parameter corresponding to the trend, we fit a few of these learnable parameters from a single time series, and we get our forecast for the forecast horizon in the future. These models, even though they're very simple, they have been used for a very long time, they're still very strong baselines in practice. So, if you talk about lots of practitioners in the industry, they're still using these models in practical forecasting tasks. These models also are sometimes interpretable, but they also have some limitations. The first one is, of course, that they have limited flexibility, which means that if there are some very complex patterns in the data, maybe you have some additional features, maybe you have some complex dependencies. Like if a user bought a product 2 weeks ago, they probably won't buy it soon, but then after some time it breaks and you have to buy some new ones, and this kind of gets combined and compounded in some complicated ways. These models won't be able to capture that. This is one big problem. And the other important practical limitation is that these models have pretty slow inference time. Because like I said, every time you want to do a forecast, you have to fit a new model. So if you have a new product that you want to forecast for, you have to fit a new model, which takes some time. And this is in general pretty slow, which is one problem with these models. These two limitations led to a different class of approaches that became much more popular in the last maybe 10, 15 years in the machine learning community, usually called global models. And the main idea here is that given this collection of multiple related time series, so again, maybe sales for different products in your shop, you would fit a single model, usually based on some machine learning algorithm. So either some deep neural network, or maybe CatBoost, LightGBM, all of these famous ones. But it would anyway just fit a single model on all the time series. And the idea is that this model has a single set of parameters that are found in such a way that the model, on average, gives accurate predictions for all the time series in your training set. Some examples of such models are DeepAR, TFT, and PatchTST. Usually these models are based on some sequence neural network models, for example, LSTM or transformers, also convolutional neural networks. And they're trained, like I said, on all the divided time series, and at prediction time, they take the new time series one by one and generate the predictions with just a single forward pass. So these models are now much more flexible. They can capture much more complex patterns than the simple local models. And also the inference for them is much faster because we don't have to retrain the model each time we want to make a prediction. Once the model is trained, we can just use it to predict many time series with just one forward pass, which is much faster than having this local model. But of course, this also comes with new limitations. First of all, we have to train this model, which takes time. And you also need to have quite some data to train these models. If you only have a single time series, you probably won't be able to fit a complex neural network model on just a single time series to generate good predictions. So this really only makes sense if you have a large catalog of products that you want to forecast. So that's why these models, even though they're quite powerful, they're not applied in all the domains. They only make sense if you have lots of data and you don't mind waiting for a long time to train these models. And kind of looking at these limitations of the two main classes of models, local models and global models, we can maybe ask the question: can we get the best of both worlds? Is it possible to have some model that we don't have to train for every new data set, for every new time series. Wouldn't it be nice if we can just take an off-the-shelf model, give it a new time series, and immediately get the predictions that actually make sense? Can we get an accurate forecast in a zero-shot way without doing any data-set-specific training? This is, of course, inspired by the huge success in NLP recently, where we have these foundation models, pre-trained models, and they're just, trained on a huge amount of data, and they can make good predictions for new tasks, for new things that you give to these models. They can give you accurate forecasts or accurate predictions. And the question is, can we replicate the success of these large language models in the world of time series forecasting? We are not the first people to ask this question, not the last. A lot of people have asked this question, and the first thing a lot of people have tried was to actually go to the LLMs from the NLP world and see if we can somehow turn them into time series forecasters. And maybe, the implicit assumption is that these models are so smart, they know everything in the world. Maybe if we ask them nicely enough, they will tell us the future. So this is what people actually tried, So in different ways, you can ask this question. You can just try to convert your numerical time series values into text, as you can see here for LLM time, and just give it as a prefix and then say, please continue this sequence. And then the model will maybe output the future forecast. You can also maybe add some more context around and say, hey, I'm trying to forecast the temperature in this location, and the last week's temperature was like that. What will the temperature be tomorrow? And then the answer is, 78 degrees Fahrenheit, I assume. And so, this is another way, which is also just doesn't change anything about the LLM, just somehow plays with how you represent the data, but the models have been trained on text before. And then going more in the fine-tuning direction and somehow adjusting the architecture of the models, people have tried to add some special tokens representing numerical values, maybe doing some kind of fine-tuning, maybe parameter-efficient fine-tuning, where you maybe tune some input and output layers, but still start with a language model and just make some small modifications to turn it into a forecaster. So, people have tried lots of things, but it wasn't super successful, and for a few reasons. First of all, these models were huge, because all these LLMs, they have billions of parameters, maybe tens of billions, hundreds of billions of parameters, and they're massive. So even if you just want to make run inference once, generate a single sequence, you often need to have multiple GPUs with state-of-the-art GPUs to even just be able to do that, which is expensive and slow. And also, at the point where you have to do some kind of special fine-tuning for your data set, and you have to train this. So for these fine-tuning models on the right-hand side here, once you have to do this fine-tuning, you have to tweak the architecture, use all these tricks, you kind of lose this zero-shot capability of these models, because the whole idea was to have a single model that I don't have to train, just give me the predictions. But if I now have to train it again, it's just a different training procedure. And if these predictions are not as good as what the traditional deep learning model like DeepAR would give me, then what's even the point of this entire thing? So, looking at these different limitations and problems with these models, we decided to try a different approach and also use large language model architectures, but treat them completely as time series forecasting models. So on a high level, if you think about it, language prediction and time series forecasting are somewhat similar problems. So this is just the overview of the model architecture. We'll get back to this later and look at it in details. The high-level idea here is that we can turn LLMs into forecasters by just working with time series right away. So the first observation that we have to make is that language modeling and time series forecasting are somewhat similar problems on a conceptual level. In both cases, we have some sequence, and we want to ask the question, how does this sequence continue? In case of language, we have sequence of tokens or words, and we want to figure out what the future tokens are. In case of time series forecasting, we have a sequence of real valued numbers, and we want to generate its continuation into the future. So it seems very similar on the surface, but of course there are some important differences, so it's not immediately obvious how to work with that. So for text, we just turn the text that we have into discrete tokens. We have some fixed vocabulary, we fit some tokenizer on the training corpus, and then each collection of character corresponds to one token, which is essentially one number between 1 and vocabulary size, and that corresponds to every part of the sentence, and we feed these discrete tokens into the LLM architecture, and this spits out the continuations into the future, and this way we can generate the text. For time series forecasting, it's not immediately obvious how to achieve the same, because time series values are continuous, and all these tokenizers that we have for text don't just work with continuous time series values. So of course, what's the how can we deal with that? What are the options? Well, it turns out we can take some very simple approach where we first scale the time series and then just discretize it by putting it into buckets, which is actually quite similar to what was mentioned today earlier in the TAPFN presentation, where essentially, we scale, discretize, and turn it into buckets. And specifically, like this consists of two steps. First, for scaling, it's necessary to kind of put all the time series into the similar range of values. Because if you think about it, maybe one time series is the temperature, which has numbers like 10, 20, 30, and then the other time series is world population, which has numbers in billions. It's very difficult for the model to kind of work on all these different scales at the same time. It's much more convenient in deep learning when we just put everything into the same range. There are many ways to do this. One simple approach that was successful before in time series forecasting that we use in this model is called mean scaling, where essentially we compute the mean absolute value of the time series over the history, and then just divide every time series value by this, and this kind of puts it into a reasonable range of numbers. After we apply the scaling, we now just do quantization or bucketing or discretization, whichever way you want to call it, which essentially just means we look at a large enough interval, for example, from -15 to 15. We divide it into evenly sized buckets. So here we have 4,000 buckets in total, covering this interval from -15 to 15. And we just see into which bucket each value of the time series falls. And we convert the continuous value of the time series that we're discretizing into the ID of the bucket. So, if this, I'm not sure if you can see this. Yeah. So like if this time series value here corresponds to bucket number 2,400, it just means we replace this continuous value by the integer 2,400. We do the same thing to all the time series values, and we just now have the sequence of integers which encodes our time series. And that's it, essentially. End of presentation, almost. Once we turn it into the sequence of discrete tokens, we can just use the existing LLM architectures, or like anything that can generate text, to also turn it into a time series forecaster. What happens, we take these context tokens that we obtained after scaling and quantization, we feed them into the language model, and this language model gives us the categorical distribution over the next token in the sequence. And each token essentially corresponds to some continuous value among these buckets. So maybe the center of the bucket specifically. And we have this distribution over here. So we know what the true value of the token is at training time, maybe 2,350. We see what the log probability of this token is assigned by the model. We can do the log likelihood. This is our loss function. This is the training objective. Cross entropy, exactly as in the language models. So essentially, the conceptual picture here is that we have our time series data set of continuous sequences. We turn them into tokens using scaling and quantization, and then we just take this data set and train it as if it was a regular language model. So everything the same, we can use the same libraries, like Hugging Face transformers, Hugging Face accelerate, whatever your favorite ones are, maybe some different ones. And for training these models, we train it, and then this language model can now generate tokens that actually corresponds to time series values. So at prediction time, we can just take our history that we have observed, the blue tokens here on the left, feed them into the language model, and generate future continuations. So essentially, each sample from the model is one possible time series trajectory. We know the model spits out these tokens, a sequence of these tokens for every value in the forecast horizon. We then do lookup from the buckets that we had before, and then we do scale it back up by the scale of the historic time series values, and we end up with this one single trajectory of the future time series value. So it's one possible continuation of the time series. And after we do that, we can, we don't have to do this once because it's not a deterministic process. Every time you query an LLM, it will give you a different continuation. You can repeat this process maybe 100 times or 1,000 times, and this way you get, many possible future trajectories, and then you can just turn these many trajectories into a probabilistic forecast. So for example, you can compute the average value for each time step, you can compute the quantiles, you can ask all the different questions that you want to ask about the future, and this will be your probabilistic forecast. So putting everything together, essentially, we don't have to modify the LLM architecture at all. All we change is we have to change how we represent the data by turning it from continuous values into discrete tokens, train LLM in the usual way, and then we can do probabilistic forecasting this way. So right out of the box, we don't have to make any special modifications to the LLM architecture. This purple box in the center, it's exactly the same LLM architecture that you can use for text generation, just now trained in a different way. And we trained it completely from scratch on time series data, so not treating it as a language model, but just kind of, we can think of this as we have a special language, which is, I don't know, language of time series, and we have sequences from this language that we obtained using our quantization scheme. Of course, it's not the end of the story. It's also very important to have training data, because if you don't have training data, you cannot train the model. And this was like one of the largest challenges to overcome throughout this project. So we started by collecting a large collection of time series datasets, and the open source ones where you can train the models and actually, with good licenses and everything, but covering a very large number of domains. So again, finance, retail, energy, transportation, some kind of mixed time series, all the different ones, which ended up in about almost 1 million time series with almost 100 billion observations, which is pretty large by time series standards, but it's still tiny by the standards of large language models that are trained on human text, where it's like many orders of magnitude more data than what we have in here. So to kind of overcome this problem and see if we can somehow enrich the data set, we also explored two ways to increase the diversity of the data and increase the effective size of the training set. And the first one was an augmentation method for time series, which essentially what it does is it combines different time series from the data set to give us some more complex patterns. We call it TS mixup. It has some math here on the left, but it's actually a very simple procedure that is also very easy to understand. First, you pick a number between 1, 2, and 3 uniformly. Then you select this many time series from your data set, maybe from different data sets. Maybe we have one time series from the energy domain, one time series from the retail domain. You then sample the weights for each of these time series in a way that the weights sum up to 1. So for example, taking the Dirichlet distribution, and then we just take this convex combination of the time series. And you can see an example here on the right. So you see we have first we have 2 time series with different seasonal periods, then we have 1 time series with a trend. And when we sample different weights, shown by these black arrows in here, we end up with new time series that, again, have new seasonal periods and also have a trend in case this trend time series was included in there. So essentially, this way, by just mixing and matching individual time series, we end up augmenting our training set and increasing the amount of training data available for us. And the second part is synthetic data generation, where we try to use Gaussian processes to generate new time series. And the idea is the following. We start with some kernel bank, where we have a few dozens of different kernels, maybe the linear kernel, RBF kernel, some periodic kernels, sigmoids, etc., a bunch of them. We sample the different kernels from the kernel bank. And then with these kernels, we sample a Gaussian process, with a combination of them. And this, again, results with some new time series that have some patterns. So they can be periodic, they can have trends, they can have some combinations of these different properties. And this way we, again, get new time series that are somewhat representative of what we think real-world time series should have. We know that real-world time series have seasonality and trends, which is what these kernels essentially from the kernel bank kind of incorporate. And this way we are able to generate more synthetic data and effectively increase the training size of our training set. Now, after we created all these datasets, we trained several model variants, and we used the T5 encoder-decoder architecture. We also had some experiments with other ones, but this was the main one that we released in the end, based on the encoder-decoder T5 architecture. It's essentially just a transformer that first encodes the historic values with a simple transformer with some special things about the biases, etc. But it's essentially just off-the-shelf NLP architecture that we tried in here. The model also comes in different sizes, so we just try to train different ones to see if the model size also has an effect on the performance in the end. But in the end, it was just these 5 models on the T5 based on the T5 architecture, trained exactly using the strategy that I described so far in here. Before we move on to the evaluation and talk about how well this performed in practice and how well this did in the benchmarks that we consider, I also, of course, want to mention that we are not the first one, not the last one, who actually trains models pre-trained models for time series forecasting. There was right before we released ours and right after we released ours, a few more papers came out from different ones. So from Salesforce, Google, CMU, Nixla, some other open source packages, like many of them also ended up being open sourced after we released Chronos. But in general, it's a pretty active field where lots of models are being released out there. And in our paper, we try to benchmark against everything that was available at the point of submission. So, but an important difference between our architecture and all these different ones that I mentioned here is that for Chronos, we really just used out-of-the-box LLM architectures without any changes to the architecture itself. We only changed how we represented the data and how we trained it and how we enriched the data set. But all of these models in here, they have some time series specific design choices. So you can think of these more like scaling up the existing deep learning architectures like DeepAR or Temporal Fusion Transformer, but just scaling them up, training on a bigger data set, which is quite different from Chronos, where it's really just, we kind of ask the question, can we just use exactly the NLP architectures for language models and use them as forecasters? And in the evaluation, we compared Chronos to all these different competing methods. So starting with the pre-trained models that I showed on the previous slide, from LLM time, forecast PFM, like Llama, Moira, and TimesFM, so everything that is open source and easy to use. We also trained it, compared of course to all these task-specific global models that were trained specifically for each task. This mostly includes these global deep learning models that I showed before, like PatchTST and DeepAR, but also has this one example which is called GPT-4 time series, which is a representative of this class of models where people take an existing actual GPT-2 architecture and fine-tune it on time series forecasting tasks, but they use the language model initialization. But again, it's more of a task-specific model because you have to fine-tune it on each data set to actually get any predictions. And of course, we also look at these local models, so statistical approaches, simple baselines, like naive and seasonal naive, and also the classic forecasting models, AutoETS, AutoRima, AutoTheta. And we ran quite a few comparisons in our paper, but I will show one here. This is quite a large figure, so let's take a second, to process what's going on in here and what these plots here show. So first of all, we evaluate two types of forecasting performance or forecast accuracy. Remember, I mentioned before we can have probabilistic forecasts or quantile forecasts where we give it where we predict the range of possible outcomes. For example, we predict the 10th quantile, 20th quantile, et cetera, and this kind of tells us about the different ranges of outcomes. This is what we have here on the left, measured using the quantile loss. And on the right, we have MACE, which is a point forecast metric, which just tells us where we only consider a single prediction of each model. So the median of all these samples, this would be one single number for the forecast horizon. And these are the two main types of tasks that people have in time series forecasting, probabilistic forecasting on the left, and point forecasting on the right. Now, the way we actually report the numbers in here is we first, for each data set among these 29 data sets, we run the baseline model, which is seasonal naive, which is actually a pretty good baseline that in many cases shows relatively strong results. And we compute the error that this method achieves and set it to 1. So essentially, the score of 1 means our method achieves exactly the same score as seasonal naive across all data sets. A score higher than 1 means our method has worse error than seasonal naive, so it's bad. And the score less than 1 means the method is better than seasonal naive. So essentially, the lower, the better. And the number of 1 is the baseline that everyone agrees is a reasonable first thing you would try on any data set. And then looking at the individual methods, we have different classes of these models in here. First, we have the local models shown in blue. So it's the baselines and statistical models. We have task-specific models shown in pink, where we train a separate model for each data set. And then in purple and green, we have the pre-trained models that did not do any dataset-specific training or tuning. So we just take the same model with the same weights and just make forward pass, get the predictions, and use that as as our final forecaster. And we can see, once we understand what's going on here, we can now look at the figures and actually see some patterns and understand some results. So first of all, we see that the local models shown in blue, they in general are less accurate than the pre-trained models and then there's task-specific models, which kind of makes sense. So they're definitely better than the baseline most of the time. You see, it's usually less than 1, but they're not as good as these task-specific models and the pre-trained models. Now, when we look higher up the list, we see that in general, of course, task-specific models like TFT and PatchTST, they often achieve the best results. So on the left, we see for probabilistic forecasting, TFT is really strong. On the right, for point forecasting, PatchTST and NHITS are the best models. But we see that right after them, we have Chronos Large. So this essentially means that like once we take this Chronos model trained in our way, just take it off the shelf, don't do any fine tuning, just like use the same model to generate predictions, it ends up producing forecasts that are almost as good or like extremely close to being as good as the forecast of the best state-of-the-art deep learning models trained on these data sets, which was quite a surprising result. I think when we started this project, we did not expect to reach this point. We were thinking, okay, maybe if we can be as good as ARIMA, this would be a huge win, because if you can do ARIMA without training, just with one forward pass, this is great. Turns out we can not only do better than as good as ARIMA, we can do much better than ARIMA and as good, or like almost as good as the best state-of-the-art models. These are all zero-shot data sets, so the Chronos models have not seen any of these data sets anytime serious from these data sets at training time. This is all like proper zero-shot evaluation on new unseen tasks, and this works really well. In general, the larger the model, the better its accuracy is, which is, I think, a sad but like not very unexpected finding that people have also seen in other cases, like for NLP models. Typically, the larger the models, the better they perform, typically. And in terms of the ranking with other pre-trained models, we find that Chronos usually has a consistent edge across other pre-trained models like Moirai, LLM Time. What else do we have here? Yeah, I think those are the ones that are shown here. I think in the paper you might be able to see even more recent plots, which has some more models in the latest version of the paper. But in any case, we see that Chronos models also have like a small consistent improvement over these other pre-trained models, which overall was very nice, very encouraging result. Where essentially, the main takeaway message that we have in here is that we can have one pre-trained model that doesn't need any data-specific tuning, that works as well, almost as well as the best task-specific models for these data sets, which was very nice. And also important thing to mention here, the Chronos models themselves, they're completely open source. So everything about the models you can find online and download for free, with very permissive licenses, both the training code, the inference code, also the code for evaluation. So if you want to reproduce these benchmarks and see for yourself, also the model weights, the actual training data sets and the evaluation data sets, it's all available on GitHub and Hugging Face. So very easy to get started and see for yourself. You can also, if you want to try out Chronos, I think one of the easiest way is to use AutoGuan, which maybe my biased opinion, because I'm also developing AutoGuan, the time series forecasting capability in AutoGuan. But their Chronos models are also in there, so all the different model sizes, very easy. You can just give your data frame with your time series, and you will get the forecasts in a single line of code using AutoGuan. It's in there. And also, a very nice recent development, the Chronos models ended up picking up adoption quite quickly. So right now we have more than 60 million downloads in Hugging Face, and this is a top 3 ranked models at all on Hugging Face, across all modalities, which was quite a huge surprise for us. Maybe, I don't know, someone out there just has a server where they just keep saying download. But in any case, a very nice surprise that how quickly we went from essentially there were no time series pre-trained models at all 1 year ago to now it's top 3 model of all models on Hugging Face is a forecasting model. So I think the field itself is growing very fast, and probably a lot of more models will come out because it's a relevant problem that people end up caring about. So at this point, maybe you will ask, okay, great, we've seen very nice results. Does it mean that we are now done? Have we solved time series forecasting? I think no, that's not the case. What we have done is we have found a very powerful recipe, which essentially means if we have lots of data, we have a large model, we can get an accurate predictor out of that, which is not very surprising. But what we have seen is that this also, we knew that this holds for text, we knew that this works for images, we also knew that this works for tabular data, but now we know this also works for time series forecasting, which is maybe not very unexpected, but very nice nonetheless. Maybe the immediate thing that we will ask after this is, can we just follow what people have done in other fields such as NLP and just scale up the data set size, crawl everything that we can crawl, train bigger models, and just have one huge model that is the best forecaster of all the time and solves all the forecasting problems? Maybe no. I'm sure that some people are trying to do that right now. And maybe I think there's definitely some room for improvement over Chronos, because even now, with Chronos and all these existing models, these are still very small. And not so they are just getting started. Maybe there are some small architectural tweaks to do. Maybe there's something special about the data. Maybe there is something about scaling the model size that will lead to some improvements. But I don't think that this will completely solve time series forecasting, where like we would just, in the future, there will be like GPT-4 for time series that everybody uses. I think it's going to be very different. And I think that AutoML has a very important role to play in this future of time series forecasting and the pre-trained models. And the main reason why I'm convinced that this is the case is the fact that these pre-trained models for time series forecasting are actually tiny by the LLM standards. So these LLM models, their sizes is in gigabytes or like tens or hundreds of gigabytes. They're huge. You need to have like many GPUs, many state-of-the-art GPUs to run them. But these models you can fit on a single consumer-grade GPU. And probably in the future we'll be able to make them even smaller, where it's going to be super cheap to just run it on your laptop, which is a huge difference from having these massive models that kind of need to have all the knowledge of all the text in the world. They need to know, I don't know, what each city means or like what happened in different years, like to generate plausible text. But for time series forecasting, I feel like there's like a lot less knowledge to put into these models. So likely in the end, they will be much smaller. And they are smaller nowadays. Which of course, opens a lot of really cool opportunities for us as like, researchers and people who are developing stuff around these models, just because they're so small. So maybe, even if you just have, even if in the end we end up with this like one small pre-trained model that works very well, maybe, today we have some model that is the best model ever, there are still many things that we can do around this model and that will lead to better forecasts. If you just take an off-the-shelf model like Chronos nowadays, of course, it's very convenient. You don't have to do anything. You just take the model, you apply it, you get your forecasts. You don't have to, as a software engineer, you're very happy because it's much easier to integrate into your workflow. But if you care about increasing the accuracy to make it as high as possible, there are lots of things that we can do. First of all, maybe things like pre-processing, like scaling the data. There are different ways to do this. There are some nonlinear transformations like box-Cox transformation, filtering the outliers, power transforms, lots of different things on pre-processing side that can change the model behavior and improve the forecast accuracy in the end. There are also some things about the model or like post-processing of the model that we can do. For example, we can fine-tune the model. This tends to help most of the time, and some preliminary results that we have in the Chronos paper also show that even like a small model that is fine-tuned is consistently much better than the largest model that was used in zero-shot way. So fine-tuning is important, and it has to be part of the workflow if you want to increase your accuracy. And also there are lots of other techniques or tricks like calibration, conformal prediction, where essentially you just take a model as a black box, you look how it behaves on new validation data, and for these models, all the data is validation data because they were trained on some other data sets. And now we can use these new techniques with these models and improve their performance further. Now they're better calibrated, now they achieve better forecast accuracy, which is great. And all these different parts, this is AutoML, right? Even if the model itself is pre-trained, we don't have to worry about training the model, we don't have to worry about finding these hyperparameters. We can just do stuff around the model, which people need, which we need to do, and this will be AutoML. And of course, it's not just, this is only if we have a single model, but I think it's very likely that there won't be a single model that works best all the time. I think we have seen this over and over again, where it's for different tasks, we need to use different models. And since these models are really tiny for time series forecasting, and probably saying that for TabPFN, I think you mentioned that for a smaller model compared to this LLM scale, we can have many different models, and then as an AutoML system, we can try out different models, combine them together, try out different pre-processing techniques, do some kind of adaptation with fine-tuning, calibration, doing some kind of ensembling. And also for time series, there are lots of ways to do ensembling, from boosting to stacking, these linear ensembles, lots of different things to try. And we end up in the AutoML world, essentially, where we have a huge toolbox of different things to try. We have lots of pipelines to build, and we want to automate it because, as a user, people really like this. I click one button, I get my predictions. Right now, with these pre-trained models, you can get this behavior where you click one button and get the predictions. But if you really want to maximize the performance, when you click this button, a lot of things need to happen. Maybe you have to evaluate a few models, a few different pre-processing steps, a few of these adaptation methods. And this is where AutoML can step in and help. So I think in general, just because these models are really small and having more models or ensembling them is always better than just relying on a single model. For these reasons, I think that AutoML will have a big role to play in here. Then, of course, so far we've only been talking about univariate forecasting, which is only a subset of the real-world forecasting tasks. So, the first part in here is for univariate forecasting, we just have the historic time series values. Maybe I have the sales for each day of the week, for each day, over the last couple of years, and I want to forecast the sales into the future. This is, of course, fine, but in many cases, it's not all the information that I have. For example, I might have promotions. There might be some holidays that happen on different days each year. Maybe there's some additional features. Maybe the weather forecast. If I'm selling ice cream, the weather forecast probably plays a big role in my ice cream sales that I'm expect to happen in the next week. So all of these things, all this exogenous information, all these different features, they are very important, and they also have to be taken into account by forecasting models. And of course, it's with existing forecasting methods, it's simple. You just train on everything, but then you have to train, which is not zero-shot. And if you want to have a zero-shot model that can process all of these different exogenous features in a zero-shot way, that's a pretty big challenge for which we don't have a good answer yet. And I think there are some ideas out there in the literature, maybe with synthetic data generation to do some kind of in-context learning. If we train in this way, looking at viewable data sets, but it's hard. We don't have the answer for that yet, and this is also an important gap that the follow-up work has to address. And the main challenge is that the number of covariates, their types, is not known in advance. So it's not like in every data set with covariates we have exactly 3 covariates, 2 categorical ones and 1 dual valued. It's always different number, different types. So the models have to handle that, and that's not clear how to do. Now, besides just these standard situations with covariates, we also have multimodal forecasting problems where before, I think people didn't even try to touch this because these simple models like deep AR, it just if you give it some text or images, it just wouldn't work. But now that we have these very large models, maybe trained on some more complicated data sets, maybe there is a way to also take into account textual or image information about the time series that will help us to make a better forecast. For example, maybe let's say my time series is a temperature of some part of some machine at a factory, and you can say okay, the temperature cannot go above 100 or 500 degrees Celsius, or it would just break. This if you put it in this text, this model will know can take this information into account and adjust its forecast. Or maybe for sales, you can say, no, these are sales of a certain product which has these properties. People tend to buy it on days when it's sunny or something like that. And maybe just providing this domain knowledge in form of text, this can also guide these forecasting models in some way to give you better forecasts. Right now, people have to come up with different features, do some feature engineering to pull this information into the models. But maybe as we move to this space of foundation models and pre-trained models, we can just somehow fuse these modalities of text and time series, and this way end up with better forecasting models. And this is something I think whenever you once we release Chronos and talking to different people from working in different domains, the first thing that we ask you is oh, can we talk to the model? Can I just describe my business problem and tell the model what to forecast, how to adjust it? We are not there yet. It's not possible, but I don't see why we cannot get there in the future. Again, of course, the big challenge is that the data sets where we have both time series data combined with other modalities are very scarce, so we have to do something about it. But it's very likely that in the next couple of years we'll have some solution for that. And finally, for all these other domain problem types, we also have multivariate forecasting, where we don't just want to forecast a single time series, but maybe we want to forecast multiple time series at the same time, and we also want to take into account their interactions. Prototypical example would also be some kind of factory process where maybe you have temperature, pressure, speed at which something is moving. All of these things happening at the same time, and very often they influence each other. So you have to look at these interactions to make a good forecast. Currently, with the univariate models, you can of course just look at each dimension one by one. But probably not the best thing that you can do, and there is some room for improvement. But again, we need to find a way to handle all these varying numbers of dimensions and all the different interactions that can happen between them, but also an important research question for us to figure out. And finally, last but not least, I want to mention this, and I don't want to keep mentioning this all the time. I think one of the big bottlenecks right now in the world of time series, not just forecasting, anything related to time series, is of course the lack of high-quality data sets and benchmarks. And even for Chronos, a large chunk of work that we had to do was about collecting, curating the data, finding these high-quality data sources that we can actually use. And in general, it's not just something that one team can do once and we are done, we are set. I think people will have to find ways to share these data sets, share these benchmarks, which will also be very important for all these different modalities where we want to look at some maybe even not just multimodal and multivariate forecasting, but also for cases if you want to do time series classification, time series clustering, time series, what else do we have? Anomaly detection. Having high quality annotated data would be important to enable these new use cases. And of course, it's not just about collecting a huge data set, putting it on Hugging Face. It's also about maybe doing science about the data for time series forecasting. So there are some important questions that we can ask. For example, how can we quantify if our data set is diverse enough, if it captures different patterns that are present in the real world time series? Do we know if it's a high quality data set or if it's just garbage? Maybe somebody puts a data set which has, I don't know, 1 billion time series, and you say, okay, is it a good data set? It's just like, if it's always the same, I don't know, sine wave repeated 1 billion times, it's not very useful. But like, how can we, somehow mathematically quantify the quality of these data sets and how useful they are for training these models? This would also be important to answer. Synthetic data is a big, place where you might get some improvements to existing models. Right now, like we have seen for Chronos, like we also did some ambitions in the paper, addition of these synthetic data sets really improves the performance, whereas like 10% of the data is synthetic. This works better than just only real world data. And we have also seen, like, if we, like, in some proof of concept works, where we can just train fully on synthetic data and still get some decent performance that is better than these statistical models. Not quite as good as Chronos right now, as the largest Chronos model right now, but still decent. But in general, it is possible that for time series, we can actually write these high enough quality synthetic data generators, and this will allow us to completely sidestep this problem of how do we collect huge collection of data sets with covariates if we can just have a good synthetic data generator. But of course, how to do that, it's a very big open question for which we don't have the answer. Maybe something like, again, like TAPIFN, we've returned to this, like these ideas with structural causal models. For time series, it's even more tricky because I think that, for example, for TAPIFN, we have a structured causal model, but it's only for a single instance. In case of time series, we can also have dependencies across different dimensions and in time. So maybe, not just the weather today influences my sales of something, but maybe the weather 2 weeks ago also has an effect on what's happening right now. So it's like the space of these possibilities grows exponentially, where you have lots of dimensions, lots of features, lots of ways in which they can interact with each other. And like, how do we write these good data generators that capture all of this diversity and then end up result in models that generalize to the real world time series data sets? So a lot of work to do in this space. And of course, like the question of how to evaluate these models, it's still, I think, a lot of things that people are doing like have some limitations. So we have, as a community, to figure out how to do that better and what the best practices are and make sure that they're shared, which is very important for us to measure progress in a consistent way and understand which ideas are good and which ones are not, and where to do more investigation. So before we conclude, just want to give a huge shout out to all the co-authors and all the people who worked and contributed to the Chronos project. Mentioned here, thanks everyone, and you can also check the names in the paper. And finally, as a short summary, hopefully I was able to excite you about the field of time series forecasting. Maybe this is something you will explore at some point in your projects and think about more. There's right now, I think we are in a good stage where we have seen that there is this huge new field of pre-trained zero-shell forecasting models. They already show some very promising results that are comparable to the best thing that people were able to produce in the last decade. But now, of course, we can move further and get even better. We have looked at the Chronos model, which essentially turns LLMs into time series forecasters by formulating forecasting as this next token prediction problem. And finally, in the last part of the talk, we have seen there are lots of important, exciting, open questions in the field of time series forecasting, and very likely AutoML has a lot to say, and a lot to contribute to answering these questions. Thank you very much.